Okay, this lesson is about probability basics. It doesn't get overwhelmingly involved, and so this may be something that you're familiar with. First of all, we've got just some key vocabulary words. In probability problems, anything where you're not absolutely sure of what's going to happen is called an experiment. So an experiment in probability is not the same as an experiment in science class. We could say that rolling a die is an experiment because you're not sure what's going to land up, okay? When you do have a set of all possible outcomes, that set of the outcomes is called the sample space. So like on rolling the die, the experiment of rolling the die, the sample space would be 1, 2, 3, 4, 5, 6. An event is any subset of that sample space. So you might just say rolling an even number, because an even number could be the 2, 4, or 6, and that is a subset of that entire sample space. In theoretical probability, which is one that we really like to use a lot, the sample space has equally likely outcomes. So again, like if you're rolling a fair die, then rolling a 2 is exactly the same probability as rolling a 6, because there's no reason you're going to get a 2 more often than a 6. Okay, so that's theoretical probability. And so we say that the probability of a particular event would be the number of outcomes that include that event over the total possible outcomes. So consider again the probability of rolling an even number. Well, how many outcomes are even numbers? 2, 4, and 6. So that's 3 outcomes out of the total possible outcomes, and there were 6 different outcomes in the sample space. So this is just kind of hitting that again, but we will write down what these probabilities are. Suppose that we're going to roll a die one time. The sample space is 1, 2, 3, 4, 5, 6. So the probability of rolling a 3, well, there's 1 3 out of the 6 outcomes. The probability of rolling an even number, well, that's 2, 4, and 6. That was what we just talked about. That's 3 out of 6. And yes, we can reduce this then to 1/2. The probability of a number less than 5. 4 of the numbers are less than 5 out of 6 numbers. And again, we can reduce this to 2/3. A number less than 10. Aha, well, all 6 of those numbers are less than 10 out of the 6 outcomes, and that reduces to a 1. Anytime the probability of something is a 1, that means it is certain. Okay, so if it's absolutely certain it's going to happen, it will always have a probability of 1. On the flip side of that, what is the probability of rolling a 0? Well, there are no zeros on this out of all 6 options. And that comes then to 0 divided by anything is 0. Well, anytime the probability of something is 0, that is considered impossible. So generally speaking, the probability of something happens ranges from impossible to certain, which means it's going to fall between 0 and 1, and it could include those numbers. That's why all of these other ones are fractions, okay? What's the probability of getting a number greater than 6? Well, there aren't any numbers on there greater than 6, so now I can just say, well, that's impossible. So that probability is 0. And then the probability of rolling a 6, there is 1 6 on there out of my 6 options, okay? Now, rolling a die is a very common question, but so is a question in basic probability about a deck of cards. And some people aren't extremely familiar with a deck of cards, so I've got a little image here. You could easily look one up on Google. But when you've got a deck of cards, there are 4 suits. So we've got hearts, clubs, diamonds, and spades. Now, clubs and spades are both black. Hearts and diamonds are red. And then we have numerical cards that go from 2 to 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 3 face cards, Jack, queen and king in each one of those suits, and then there's also an ace in each suit. So if you're not familiar with this, then you would want to check it out. But let me also just kind of footnote that then each one of these, each one of these rows has 13 cards in it. And so when you look at it all together, 13 times 4 is your full deck. There are 52 cards in the deck. So what is the probability of drawing a king? We're just going to draw one card. Well, there are 4 kings in this deck of 52, and that does reduce to 1 out of 13, which corresponds to there being 1 in each row of 13. Now drawing a heart, this entire top row is hearts, and that row has 13 cards in it. So there are 13 cards out of 52. That does reduce to 1/4, which corresponds to it being the first row out of 4 rows. Now, a face card. Okay. That would be Jack, Queen, or King. So 3, 6, 9, 12. There are 12 out of the 52. And that does reduce, and you might expect this now, just like the rows, there's 3 in each of the rows, and every row has 13 cards. Now a red ace, that means it had to be an ace in the hearts or an ace in the diamonds. So there are 2 red aces out of all the cards, and that one reduces to 1 out of 26. Now, what about a president? Well, there is no card that has a president on it. We have kings and queens and jacks and ace, but no president. That one's impossible, so that one's 0. So again, if you're not familiar with cards, you might want to look up that on there. Now, I just want to say here, don't make things harder than they sound, okay? If you are given a problem and you are told that it has equally likely outcomes, or it's presented to you as equally likely outcomes, just accept it for what you're doing right now, okay? Don't do any of this argumentation for the sake of it. Technically, on a coin, there is like one side of it has a little bit more metal than the other side, and it's not exactly half and half, but it's really, really close, and so we count that as half and half. The dice that you're presented, you will assume they are fair dice, okay? The cards, it's a brand new deck of perfectly fair cards. The spinners are not bent. I mean, so no matter what's going on, if it's presented to you as having equally likely outcomes, let it go and assume it is. Now, besides our theoretical probability, we have empirical probability. And empirical probability isn't based on what could happen, but really what did happen when somebody was making observations. So it's just, the difference might be, instead of saying, well, if I flip a coin, it's a 50% chance that I'm going to get something, it's saying I flipped the coin and I got heads this many times or something. So this one has to do with past. You can see here that both of these are past tense words. It was observed times that something occurred, and the total number of observed occurrences, so it's often in the past. Now, a lot of times you find out with this information presented in tables, because a lot of times people just keep track of it with tally marks as they're going along. But this one is certainly more complex, and it's the marital status. And you might say, well, how are they going to observe the marital status? Well, this actually came as the result of then a survey. So, but it's a past tense. It's not just something that happened. So the result of a survey also falls underneath this type of probability. If it's in a table, if they don't present you a total row and column, it's recommended you make one so that you can know what your denominators are going to be when you're doing probability. This one does have a total on it, and the total horizontally on this total row and the total vertically should match, because it doesn't matter if you're saying male first plus female, or married plus never married plus divorced plus widowed, it both comes out the same. Okay, so now if one person, to do probability from this, you just really look at how many times it happened out of the total. If one person is randomly selected from the presented population, so from the population in this particular thing, what is the probability the person is divorced? So you're looking at how many people reported they were divorced. And that's total, so we've got 26 there. Out of, what was the total population here? 254. Now, one thing I don't know, I have to say this because you might also find this disturbing. It's talking about the adult population, and then it says ages 15 or older. So not quite sure that goes together, but we're going to let that go. We can divide both. I don't know how this reduces really well, so let me show you on your calculator. I know I can divide them both by 2, but a little handy trick on your calculator is just to enter it as a fraction. So we get 26 over 254. And notice when I hit enter, because I'd already entered it like a fraction, it automatically reduced it for me. Now, if you enter it like division, 26 divided by 254, it's going to give you a decimal. If it gives that decimal, you can immediately hit math, enter, enter, and it will again convert it. But if you'll just start by entering it as a fraction, when you hit enter, it reduces it for you. So this reduces to 13 over 127. So it was really just divisible by 2. Okay, what is the probability the person is female? So part B is different, so we want to get the total number of females. So this one, the total number of divorced came from a column, but the total number of females will come over here from this row, and it's 131. And again, that's still out of that total of 254. So that very well may be the reduced fraction, but I'm just going to check. So math, not math. That was from a different lesson. So we have alpha y equals, enter, 131 over 254. And that gave me the same number, so I know that that is reduced. Nothing else to do there. Okay? Now, there's one other concept really within this, and it's called the law of large numbers. And it's not an accident that I have a casino in this picture here. The law of large numbers is why casinos make so much money. Okay? If you just look at it, let's back up and talk about the law of large numbers with coin flips. We know that theoretically, when you flip a coin, you should get heads 50% of the time and tails 50% of the time. But if you actually take a coin out and you flip it, when you flip it 10 times, it would actually be pretty unlikely for you to get 5 of each. If you flip it 20 times, it's still unlikely for you to get 10 of each. So how many times do you have to flip it before we actually start getting heads about half the time and tails about half the time? Well, this is one possibility of the chart that happens. You know, you flip it 10 times, maybe you only have heads 30% of the time. Suddenly you're going to get heads a lot of times in a row, so that by the time you flipped it 30 times, you've gotten heads more than 70% of the time. But as you can see, this is almost kind of like an average too in a class. When you very first start a class, your very first grade will either be high or low. And so as you do a few grades, it really kind of, but as we get lots and lots and lots of grades in there, it levels out to a particular average. So the more we have flips, the more flips we have, it starts to level out at that 50%. And so that's the law of large numbers at work. And what happens then is that when we are doing probability based on what has happened in the past, with a very few number of trials, it may not match that theoretical probability. But as you increase the number of trials, and that's what's in blue here, is the number of trials increases, empirical probability, based on observation, will get closer to theoretical probability. Okay, so that's the law of large numbers. So then thinking about that in terms of the casino, oh, this is still about the large numbers. It's just talking about the coin flip there. But I want to take that back just for a minute then to the casino and just mention that. The reason the law of large numbers works for them is because they have so many games happening, and the odds, the probability of you winning on one particular spin of the roulette wheel, or one particular hand of blackjack, or one particular pull of something is really low. Yes, it could happen. If it happens for an individual, they're very excited about it. But because they have so many games happening, they certainly have the law of large numbers at work. And the law of large numbers is going to say that all of these trials and experiments then will end up leveling out to what the theoretical probability is. And the theoretical probability of you winning a game that's based entirely upon chance is very, very low. And so that means the theoretical probability of it turning out in the casino's favor is very high. And that's why for an individual, they may have a good night, but in the long term, it's the casino that's definitely going to win, and that's due to the law of large numbers. Okay, so this lesson is about basic probability. Get in touch with me if you have any questions. Use that Ask My Instructor. Hope this is helpful.